Hello, today I would like to briefly review the development of scale estimator. I'm Tobang Lee. I studied in quantum technique and took in Berkeley course now. And when we consider scale estimator, we do some calculations among observations to estimate the population dispersion. The dispersion is that because in statistics, for any population, it is almost impossible that every values are within are the same. So a population is that if we try to measure how different is the values relative to the center, relative to the average. And then you can see, for example, the red population, most values is very close to the center, but for the blue population, there are many values far away from the center. So the blue population has a much higher dispersion comparing to the red population. And in statistics, sample range might probably be the first approach to study the dispersion. It is pretty straightforward, just the largest minus the smallest. But this approach has many drawbacks, and the first is that the maximum and minimum values, as we said previously, they are very sensitive to outliers. They are not robust, and also many common probability density functions are unbounded or partial bounded. For example, the Gaussian distribution, Laplace distribution. I mean, that means their population range is infinite. So although if the sample range might sometimes it can also reflect the changes of dispersion, but then it becomes an ill approach because it is not consistent. And also, even if we consider that it is bounded, but then it is possible, for example, here is another. These two distributions have the same population range, but however, the red one obviously is more dispersed than the green one, right? Because there are more values that is far away from the center. So that the population range cannot reflect these changes. So if we consider the average cases, it is another very natural approach, so it is called the sample standard deviation, and this concept was closely related to root mean square error and the central limit theorem. So it was developed in the early of 19th century. And here is a mistake. This is the population standard deviation, not sample standard deviation. But ignore that. And the standard deviation just consider all the values relative to the mean. The mean might be population mean or sample mean, and then square it, and then take the average, and then take a square root of it. So or if we slightly modify it to consider the absolute deviation instead of the square, and then we can obtain a sample average absolute deviation. Or Gauss suggested a root mean square deviation from the mode, but the sample mode is very difficult to compute. He only considered the population case, and these estimators are proposed in the early of 19th century, and they are not robust. And the sample interquartile range is probably the first robust scale estimators. It was proposed by Galton in the late of 19th century. And this sample interquartile range is a modification of the range, and instead of consider the maximum and the minimum, they consider the medium, and consider the differences between the 55% percentile and the 25%. So this way, first it is not sensitive to the maximum and minimum. It is robust, and also even in this case, for example, they have the same bound, but this because it is closer to the center, so these changes can be detected using interquartile range. And the sample range and interquartile range, and they are all a class of scale estimator. We can call it quantile differences. And another robust scale estimator was first popularized by Hempel, but he credited the ideas to Gauss in 1816. And this method is replacing the average absolute deviation in the mean with medium. And then here is took the mean of all this absolute deviation, and then instead we consider the medium of all this absolute deviation. So it is called sample medium absolute deviation. In in 1976, and Bickel-Lehmann, they generalize all this estimator standard deviation, average absolute deviation, or median absolute deviation. They generalize this estimator as a measures of dispersion, and now in economics it is often called Bickel-Lehmann dispersion. And this Bickel-Lehmann dispersion is they stochastically, their definition is that stochastically they consider all the values relative to the population mean. If it is stochastically, the absolute value is larger than another distribution with the same measures, and then we can call it and then this distribution is called more spread about this than another distribution. So but they have a symmetry assumption, because if we consider the median only in the symmetry case, then it is asymptotically coincide with the mean. Otherwise, it is not. There is a bias, so this might become an ill approach. So to tackle this symmetry assumption, later they considered another approach, a very novel approach called measures of spread. And instead of considering the relative differences of all values relative to a mean estimator, they consider all possible differences. For example, 1, 3, 5, 7, 9. And then it is 1, 3, 1, 5, 1, 7, 1, 9, 3, 5, 3, 7, 3, 9, 5, 7, 5, 9, 7, 9. Okay. All these possible pairwise differences, if a distribution is for all these pairwise differences and to another distribution, the corresponding pairwise differences are all greater or equal, and then this distribution they can call it more spread out than another distribution. And this concept was probably first introduced by Braun and Turkey, but an estimator was proposed even earlier than that, called by Guinea in 1912. He considered the mean of pairwise absolute pairwise differences. But Bickel-Lehmann were the first to generalize this class of estimator, and they can deduce other estimators that are very important. For example, here they consider if we square all these pairwise differences and then take the mean of this of the result, they call these pairwise differences as pseudo sample, because this is the sample, and then you took all these pairwise differences, they consider as pseudo sample. If you square all this pseudo sample and then take the mean of this of the resulting squared pseudo sample, and then you took a square root of the mean, and then they show that this value is equal to the square 2 times the standard deviation. So this is a very surprising result, because it shows a different measures, different method computing the standard deviation, because previously the standard deviation is considered all the values, all the possible values related to the differences related to the mean. But here it is the pairwise differences. If you're using this way, it can also equal to the standard deviation. And then in this, and then they, in the final section of their paper, they show that an advantage of this approach, that it is possible to robustify the standard deviation with this approach. For example, if you talk, just like the Hodges-Lehmann estimator or weighted Hodges-Lehmann mean using a weighted average to estimate this pseudo sample, they use a trim mean to estimate this pseudo sample to achieve a robust standard deviation, or called trim standard deviation. And indeed, this approach is much better than the Bickel-Lehmann dispersion, because if we try to robustify, for example, the standard deviation with this definition, and then you must first replacing this mean with a robust estimator, for example, median, and then also there is an average. This is the average, and then you also need to robustify it. So the result will be very similar to the median absolute deviation. It is just median square root deviation. The problem of median square root deviation is that, for example, if you consider the median is here 5, and then 1 to 5, 3 to 5, 5 to 5, 7 to 5, 9 to 5. Okay. If you consider these differences, there is an issue that, because the central limit theorem already guarantees that for the variance of sample mean is closely related to the sample size, the standard deviation relative to the square root of the sample size. So, and more importantly, this principle can be extended to other mean estimator, for example, the medium, and they call it asymptotic normality. So generally, for mean estimation, if the sample size is directly negatively related to the variance, and since the sample size of the pairwise approach is much, for example, 5 choose 2, right? Here is just 5. It's much larger than just the sample, then the relative differences related to a mean estimator. So this pairwise differences approach, generally the Bickel-Lehmann spread should have a much better efficiency comparing to the Bickel-Lehmann dispersion. And indeed, this was also later verified by Rousseeuw and Croux in their alternative to medium absolute deviation. And they show some examples that this pairwise differences approach is much better than the medium absolute deviation in terms of variance. And they further propose, Bickel-Lehmann proposed in their paper, they also propose a medium of pairwise differences, absolute differences. They further propose a class of estimator called the medium of mediums of pairwise differences, for example, 1, 3, 5, 7, 9. And then you first consider 1, 3, 1, 5, 1, 7, 1, 9, and then 3, 1, 3, 5, 3, 7, 3, 9. Anyway, all this, every group, you consider the medium, and then the medium of medium, this is their method. This method, although it seems that the time complexity is n2, but they suggested an algorithm whose time complexity is n log n. And that means this method is not only statistically efficient, have a similar efficiency as the medium of pairwise differences, but it is also computationally efficient. Therefore, this paper is very popular in biostatistics, have more than 2,000 citations. And